And here we go. We're going to see how much we can do. I guess technically we're already a day behind because we should have started this the 16th, but that's okay. Not a big deal. Not a big deal. We'll catch up pretty quick. All right, let's see if we can do this, guys. These are properties of limits. So they're just saying here, this is coming from your textbook that we have. I know no one checked out a textbook because they're heavy. You don't need to. I'll get all the notes for you guys, all the important stuff. So it's telling you here that if I have a limit and it equals some number, so here's a function f, it equals L, and I'm approaching c, it's approaching some constant, right? As x approaches some value c of g of x, this limit is m. So it's telling you all these different rules, the sum rule. If you have the limit of f of x plus g of x, you can just add those limits. If you have the limits of f of x minus g of x, you subtract them. If you have the limit of f of x times g of x, you can multiply them. So it's just pretty much just basic rules. If you have a constant in front of that f of x, you can pull the constant out. Sometimes they'll write this one right here like this, k limit as x approaches c of f of x. And we already know that this right here in brackets is L, so this is just k times L. Don't freak out, guys. You're going to see we're going to use them right now. Limit as x approaches c of this quotient. As long as the g of x is not equal to 0, it's going to be L divided by m. And and you can square root it. You can raise it to any other power as long as it's a real number. That's the key. I want to yawn. I think it's because of you. So who did not get enough sleep? Okay, sorry. I also noticed that you guys are more alert when you guys are like doing your work, but as soon as we start lecture, like, oh, okay. Sorry. I know maybe it's a morning. I don't know. All right, here we go. Letter A. It's simple stuff, guys. It's not going to be anything crazy. They tell me that the limit of x approaches 4 of f of x is 2, and the limit of x approaches 4 of g of x is 3. So this one, according to my properties, I can just do what's g. So it's the 3 plus 5, 7. There it is. That's it. 5, 6, 7, 8. Oh, yeah. I'm going to edit that out from the video. I'll leave it. And then I'll be like, yeah. I think I heard someone say 7, or maybe I was thinking 6, 7, or I don't know. All right, here we go. This one right here. This one's a little tough, guys. Limit of x approaches 4. I have a number in the front, and this is called direct substitution. So we can do 4 times f of x times whatever that limit is. The limit of x approaches 4 for f of x was? So we can go 4 times 2, which is 8. Right here. I did direct substitution. See how there's an x there? And what is x approaching? So 4 times 2. That's called direct substitution, guys. Here we go. This one says g of x squared. That's the same thing as writing. I'm going to write it like this. Limit as x approaches 4 of g of x squared. All right. So what is that going to be? Yeah, 9. That's it. Notice once you put the number, you no longer have to say the word limit. This one right here, we're going to do direct. Well, here we go. What's the limit of x approaches 4 for g of x? 3 over, and then the limit of x approaches 4 for f of x. So 2 minus 1. So it looks like this is just 3. And there it is. That's it. Cool or not cool? Darn it. Okay. Here we go. We're going to continue with properties, and we're just doing the same thing. Limit of x approaches c for f of x is 3, for g of x is 5, for h of x is 2. Y'all ready? So this one right here, limit of x approaches c is going to be 3 plus 5 times 5. So it's going to be 28. I was going to say 27 to joke, but you guys would probably be like, you did that. Okay, I'll stop. All right, here you go. I can't even talk right. Limit of x approaches c of g of x raised to the third power. So I look for g of x. I'm going to write 5 to the third. 5 times 5 is 25. And if I have 5 quarters, that is 125. I don't see any issues. I think we're okay. We're still okay, guys? All right, this one right here, limit of x approaches c of f of x is the square root of 3. If f of x would have been negative, it would have been does not exist, but that's not the case here. All right, on this one right here, let's see. So 5 times 2 over 3. So 10 over 3. And that's it. See? Not that bad. Was that tough or not? No. Use the graph of the function f of x shown to the left in order to determine. All right. So what does that little plus symbol mean from the right? So I look at the curve as I approach 6 from the right. What is that limit? Yeah, 3. Limit as x approaches 6 from the right is 3. And that's it. Do we feel okay? Look at that. We just finished 2 pages like nothing. Let's go to page 3. 3. A function f is shown to the right. Determine the equation of all vertical and horizontal asymptotes of f and the equivalent limit notation. So I hope if you haven't gotten the chance to see notes 1.5, this could be tough. Thank you, miss. I did fix the notes. I noticed that more and more this laptop is starting to make errors. Sometimes it records my audio but doesn't record what I annotate. Sometimes it does. It's working. I'll check right now to see if it's working. So I don't know. I might need a new laptop pretty soon. But yeah, check my videos. If you don't see every time it's supposed to be I'm supposed to be annotating this PDF. If you just see a PDF and it's just still, that means the data got corrupted somehow. All right. So yeah, don't worry. I'll see if I can do a cleanup on this laptop here. First, what are my horizontal and vertical asymptotes? I have a vertical asymptote right here. See, I have another vertical asymptote right here. There is no limit, There is no limit to how many vertical asymptotes you can have, but there is a limit to how many horizontal asymptotes you can have. The most horizontal asymptotes that any function will have is 2. You cannot have more than 2 horizontal asymptotes if you have any at all. Does that make sense? Write it in there. The most horizontal asymptotes you can have is 2. You can have as many vertical asymptotes as possible, but the most horizontal asymptotes you can have is 2. You cannot have more than 2. It's not possible. You can't have more than 2 n behaviors, like converging to 2 x values. All right, here we go. So my horizontal asymptotes. Horizontal. So I see that I have y equals 4 and y equals, is that negative 1? And how do I show that with limits? Limit as x approaches infinity of this function, f of x, is equal to 4. And limit as x approaches negative infinity of this function is equal to negative 1. Are we okay with that? Okay, I'm going to change colors. I'm going to write the word vertical asymptote. So let's see, I have one at negative 1. And I have another one at, is that 6? So here's how you're going to write it. Limit as x approaches negative 1 from the left of this function is equal to positive infinity. Limit as x approaches negative 1 from the right-hand side of this function is also equal to positive infinity. So that took care of the negative 1. Now I'm going to write limit as x approaches 6 from the left of this function is equal to positive infinity, and limit as x approaches 6 from the right of this function is equal to positive infinity. If this is not making sense to you guys, please watch that video. That will make more sense. And then after all that, if it still doesn't make sense, come talk to me. Are we okay so far? Okay. We have our first composite function. Oh, I can see you guys still writing, so let me slow down. Okay. Ready? All right, here we go. We have our first composite function. Anytime you see that, here's how you're going to do it. Limit as x approaches negative 1 of f of g of x. So first, I'm going to write the word here first. First, evaluate inside. What is inside? That g of x. So you're going to go limit as x approaches negative 1 of g of x. And I'll slow down. So I look at my g of x function. and I see what's happening as x approaches negative 1 for g of x. As x approaches negative 1 for g of x, that limit is, what do you think? What is that limit? The one on the right. It says graph of g. As x approaches negative 1 for g of x, the limit is 0. And then second, evaluate outside at this value. So you're going to write limit as x approaches 0 for f of x. There it is. So if I approach 0, this is not direction. It's either left or right. So let's see. If I approach 0 from the left, it is 7. If I approach 0 from the right, it is 3. They're different. Because they're different, what am I going to say? Does not exist. Don't worry. I'll write it down right here what I did. We did limit as x approaches 0 from the left of this function. And we got 7. And then we did limit as x approaches 0 from the right of this function. And we got 3. They don't match, so it does not exist. Are we still okay? Don't worry, guys. We're fine. Okay. I need to switch to example 5 and example 6. So next time I'll switch. Okay. All right, here we go. So I'm going to do g of x first. So I'm going to write limit as x approaches 4 of g of x. So if I approach 4, that limit is, what's that limit? 0. So I'm going to put 0. So now that I got that limit is 0, I'm going to go limit as x approaches 0 of f of x. So if I approach 0 of f of x is the one on the left, what do we get? Yeah, I heard someone say it too. So there it is. So limit as x approaches 4 for f of g of x is nothing more than 2. There you go, guys. You did it. You did it. Okay, I'll stop. I'll stop this. All right, limit as x approaches negative 1, and I have this f of x times g of x. Well, we're just going to have to do limit as x approaches negative 1 of f of x times g of x. So this is just a multiplicative property of limits. I go to f of x as I approach negative 1. As I approach negative 1, that limit is negative 5. It's the limit, not the function it's evaluated at, where you're converging, where it's converging. All right, let's look at the other one. Limit as it approaches negative 1 of g of x, it looks like it is negative 4. So this is 20. Yes. I said limit as x approaches negative 1. I looked at my f of x. Here's f of x. If I approach negative 1, what's that y value? 5. So if I approach negative 1 from the left and the right, it's approaching that negative 5 value. I go like that. So, okay. We're still all right? Oh, where did I get the what? Yeah, hit me. No, you're good. Look at this one right here. This is a graph of G, and I'm looking for where I'm approaching negative 1. As I approach negative 1, it looks like I hit negative 4. Okay. Example 8. Don't worry, guys. We're almost done. We're going pretty fast, as you can see. Given the following graph of f of x, find the value as x approaches negative 2 of f of x minus 3. There's two ways to do this. It depends how you see it. It doesn't matter to me how you see it. So this is your graph of f of x. This graph here, f of x minus 3, is going to shift this graph 3 times to the not left, to the right. So if I shift that graph 3 times to the right, that vertical axis with negative 5 is not going to be at negative 2. Do you guys see that? If I approach negative 2 from the left, it's going to go positive infinity. If I approach negative 2 from the right, it's going to go negative infinity. You could do it that way. Another way that I've had kids do it in the past is like, Chuck, well, that's the same thing as saying f of -5, evaluating the limit of -5. And you got to be careful with that, guys, because this is undefined at -5. And I know that's what some kids say, oh, that just say does not exist. If you see it that way, that's fine. But I would recommend you look at it more like shift this graph 3 to the right and then evaluate it, what's happening at that x equals -2. So if I approach -2 from the left, positive infinity. If I approach -2 from the right, negative infinity, because I'm shifting this graph 3 to the right. Does that make sense to you guys? Yes. So this one does not exist. Did we do some questions like that on the delta already? No, right? Okay. I haven't given that one yet to you guys. You guys have done questions like this one though, I think. Use the graph of the function f of x shown below in order to determine all values of a for which the function has a limit of -2. If there are no values of a, state that there are none, or write the empty set. Empty set just means to push enter because it's an empty set. So -2 is right here, guys. I like to just draw a line. I can't draw a straight line. There we go. And so that's the y equals -2. And then I just see where the limit is -2. So it hits at all these. So limit as x approaches -6 of this function is -2. Limit as x approaches -1 of this function is also -2. Limit as x approaches 2 of this function is also -2. It looks like it has one more. Limit as x approaches 7 of this function is also -2. So there it is. So what are my values? The values that they want are these values. So a equals -6, comma, -1, comma, 2, comma, 7. We're still okay, guys? Okay. And let me know if I need to slow down. So I'm slowing down. All right. Now we're going to talk about continuity. All this means, when we talk about endpoints, if it's an endpoint, you're continuous. But if it's an interior point, so what does this mean? What does all this mean? So if you're in an interior point, this means this, okay, I guess I'll write it. Limit as x approaches c from the left of some function equals limit as x approaches c from the right of that function. So that means I have a limit. So that I can write limit as x approaches c. That means I have a limit. If I approach from the left and I approach from the right and I'm converging at the same point, I have a limit. So that's just how you have a limit. Now, what makes it continuous? This addition right here. If it equals f of c, you're continuous. Chav, what does that mean? Okay, put your pencils down, guys. I just want to make sure that you guys get this. So that means this. Look, so here's c. So just listen right now. In a little bit, I'll let you write. So at the moment, am I continuous at c? No, at the moment I'm not. I have a hole. And that's also called removal discontinuity. But I do have a limit. Yes or no? Now, check it out. If I fill in that hole, is it continuous now? Now it is, because now you added this part here in red. Now you're continuous. Not only are you converging at that point, but you're also defined there, which happens to be the same as your limit value. So this is the definition of a limit. All right, guys, go ahead and write. Well, that's why I wanted you guys to write. If limit equals the same as f of c, comma, f of x is continuous at x equals c. F of c is some value, right? You okay? Are you happy? Okay. All right, guys, here we go. There are three, well, it says four here, I guess the oscillation ones. There are three very common forms of discontinuity. This one is not as common. I mean, it still happens, especially when you do engineering and there's a lot of noise and you got to try to filter that noise out. This is called discontinuity by oscillation. Discontinuity by oscillation. Chav, what's that? It just keeps going up and down, up and down, up and down, and you can't tell. I know, see, you can't tell. It looks like it just stops, but at zero, it just keeps going, and it goes up and down so fast. Like, can you think of something like that? Let's go to Desmos. I know, guys. Let's look at some practical examples. Desmos.com. Let's graph. Sin x is nice and continuous, but look what happens if I do. Don't worry, guys. We'll stop right now. Look what happens if I do that. Look what happens to that blue curve. Can you tell where it's at zero? Heck no. It's just going up and down super fast. Super fast. So there it is. Is that sine of 1 over x is not continuous at x equals 0 because it's going so fast. You don't know. You can't tell if it's going up or down. So that's called discontinuity by oscillation. And then the other discontinuities you already know. So let's see. This is called a hole, and it has a name. That's a hole. That's also called a removable discontinuity. A removable discontinuity is the only type of discontinuity that can be made continuous. All you got to do is fill in that pixel. That's it. And it'll be continuous. Cool or not cool? The other one is called the jump. Chav, how does the jump look? A jump. It looks literally like a jump. It just jumped. Try and think of the what's the most famous discontinuity? We were talking about it a little earlier today. Starts with a letter, I guess the letter V. Vertical asymptote. If you have a vertical asymptote, what type of what do you think they gave that name? It starts with the letter I. Yep. Yeah, see, context clues. That's an infinite discontinuity. You guys are so smart using your context clues. It's an infinite discontinuity. It goes up forever and down forever. You never cross. It's an infinite discontinuity. The three big ones in AP Calc, in everything, in every subject. These are the three big ones. I guess discontinuity by oscillation is also big in engineering, but those are the three big ones that we'll be dealing with in Cal. Cool or not cool? Okay, all right. Here we go. I talk about removable and non-removable. It says all discontinuities can be classified as removable or non-removable. Removable discontinuities occur when the function has a limit, holes in the graph. Non-removable discontinuities occur when the limit of a function does not exist, jumps, and vertical asymptotes. So this is the only one that has a removable discontinuity. The other two are non-removable. There's nothing you can do to make the other two continuous. Nothing. Because then it won't be a function if you make this one like continuous. Look, that's a vertical line. Remember, you can't be a function if you have a vertical, like if you doesn't pass the vertical line test, or if you have several outputs for the same x value, it's not a function. You cannot make a jump discontinuity continuous. You can't make an infinite discontinuity continuous. You can't. If you do, you'll win the Nobel Prize because you can't. It's impossible. I'm not saying you can't win the Nobel Prize. It's impossible. You can. You guys can do great things. But okay, there it is. So it says find where the graph is discontinuous. Identify the type of discontinuity. Okay, by the way, at the endpoint, you are always continuous. I think maybe I just didn't emphasize it. An endpoint. Here it is. A function is continuous at a left endpoint A or is continuous at a right endpoint B if it's domain. So all that means is, so there it is. That means you can only approach, this is the left endpoint. Chav, why is that the left endpoint? Because you can only approach a left endpoint from one direction, from the right. So that's why it says there a plus symbol. And that equals that value, whatever that value is. You're continuous at that endpoint. Same thing for the right endpoint. So circle the one on the right hand side with the B with a minus. That's a right endpoint. You can only approach. Do you guys want a visual? Yeah. Okay. Let me write a visual for you guys. So here it is. Let's do the visual for all of them. A, B, and C. Okay. So here's your visual for all of them. I'm going to just do an x-axis. Here's my y-axis. I'm going to call this A. I'm going to call that C. I'm going to call that B. And notice, there it is. I'm continuous and differentiable. I can only approach A from the right-hand side. That's why it says a little plus symbol. And that equals f of A. Whatever that value is, that's f of A right here. Whatever this value is. If I call this f, if you call this f, then that's f of A. And then that's f of C. And then that's f of B. So there's your visual. Bam, 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 with your visuals. Okay. Gotta have some funness. All right. There it is. So, of course, on an endpoint, you're continuous. So you're continuous at -1, right? There's no hole there. What about at 1? Bless you. Are you continuous at 1? Okay, discontinuous at 1. At x equals 1, is discontinuous. What type of discontinuity is that? Jump. Jump discontinuity. And non-removable. Non-removable. All right, what about, where's my next discontinuity? 2. What type of discontinuity is that? It's a hole. What do they call that? Starts with an R. It's a removable discontinuity. There you go, guys. We're good now. See, now we just got to practice a whole bunch of that. Are we still okay? Okay. What's up? Hit me, miss.
For the hole at x equals 1, you just not write that down as a discontinuity.
Well, it's the first discontinuity is a jump. You're just that hole there. They're just doing that because I want to be defined for all x values. So if I were to tell you what's f of 1, it's 1. But the first this type of discontinuity is a jump. You know what I mean? Okay. Or are you just saying that? No? Okay. Let the record show that we're all good. Okay. That was a joke, but it wasn't funny, so I'll stop. We're okay though, right? Okay, I know. All right. Find where the graph is discontinuous. Okay, this is from delta. Where's the graph discontinuous? Tell me all the x values. -4. All right, guys, focus. 1 and 6. Between -4, 1, and 6, it says identify the type of discontinuity. At -4, what is that? That's a hole, which is so we're going to say removable discontinuity. At 1, what do I have? Jump. By the way, I don't like it at 1 because look, is this a function? No, you can't be defined at -2 and at -7. This is not a function, guys. That's why I don't like this graph, but that's what delta did, so that's fine. What about at 6? It's a irremovable discontinuity. How do we feel? Do we feel okay? Okay. Let's go to the next question. Dang, I didn't open up my polls. That's fine. I didn't open up the polls. I'll open it up for the next one for sure. All right. Find where the graph is discontinuous. Identify the type of discontinuity. So first, where am I discontinuous? -6, -3, 4, and it looks like, is that it? Okay, at -6, what do I have? Removable discontinuity. At -3, what do I have? Infinite discontinuity. Look at you guys. Infinite discontinuity. At 4, what do I have? Another infinite discontinuity. I'm just going to put an arrow. Infinite discontinuity. What's up?
Infinite discontinuity
always have a vertical asymptote.
That's why it's called infinite. Cool, right? Hell yeah, this is cool. Maybe you were sleepy a little while ago, but not sleepy anymore. I wish I had a button to push. Like, did I already tell you? Like the what is it called when we get like the fires and everything? If I had a church, I would totally have like a whole bunch of like, you know, fireworks and everything.
Oh, you need a soundboard.
How I just get a soundboard and just make random sounds and
You download Discord.
You can do it like online too.
okay.
Yeah,
I'm gonna see if I can find a
You
soundboard.
need a soundboard, job.
Yeah. Dun, dun, dun. Yeah, I do. I'm gonna invest in that.
You need like a victory one, like a wrong one.
All right, guys, here we go. Your first experience with AP Calculus exam. You guys ready? This one right here is from the 2012 AP exam, international exam. Did I give data on it? I did not. Dang. Okay, but don't worry, I'll give you data. Do you guys want to give that one a shot first, and then we'll talk about it? Okay, give it a shot. This is from the 2012 exam. Read it, guys. I'm going to be doing that. I'm going to go ahead and do that. This is Chavez. Yeah, no. What's the answer, guys? Let's see. Let's look at it. The graph of the function f shown on the right, which of the following statements is false? So they want a false one. Limit as x approaches 2 exists. That one's true, because if I approach from the left, it's 2. If I approach from the right, it's also 2. Limit as x approaches 3 exists. Yeah, that looks like it exists. It's continuous. It's just a sharp corner there. If I approach 3 from the left, it's 5. If I approach 3 from the right, it's also 5. Limit as x approaches 4 exists. If I approach 4 from the left, it's some number a little bit smaller than 2. If I approach 4 from the right, it's 4. So it looks like that one is false. Limit as x approaches 5 exists. Yes. And the function f is continuous at x equals 3. Yes. So the one that doesn't work here is letter C. Does that make sense, guys? Perfect. All right. Here's another one. You guys want to give that one a shot? I'm going to start going over it, guys. Let's see. Limit as x approaches 2 from the left equals f of 2. Is that true? Yep. Limit as x approaches 6 from the left equals 6 from the right. Is that true as well? Yes. Limit as x approaches 6 of f of x equals f of 6. Is that true? No. So the correct answer is C, 1 and 2.
Wait, why is it 3 right?
Oh, because f of 6 is equal to negative 3 because of that right there. But the limit, yeah, you got to ask, guys. Ask me. The limit as x approaches 6 of f of x is equal to negative 1. So see how they're different values? If that would have been negative 1, then that's the definition of continuity. Does that make sense? Yeah. All right, there it is, guys. We got our first notes. So here it is. Oh, what's up? Is it okay if I zoom out? So let's see what it says here. Take care of handout activity 1. So I'm going to give you that right now. So do this one first, guys. I haven't released the DM2. I'm about to in a little bit. Let me know if you have any questions. If you haven't created your UH account, please do so today. Attempt UH Quiz 1 Limits 1. We haven't done everything because we haven't talked about direct substitution. We have at the preliminary, but we haven't done it. And because I want to stay true, I'm not going to do a lesson tomorrow because that's your lab day. So tomorrow's just going to be about finishing up some stuff. So I'm going to open it up. Make sure you make your first attempt on your quiz one limits one by Wednesday. All of you have already done it, and I'm going to pick it up on Sunday. Is that a good timeline? Okay. If you feel like you got a good grasp, you can try quiz two limits two, but don't feel obligated. I'm not going to open that one up just yet. All right. So let me pass out that activity. It's a pretty easy activity. I think you guys will finish it pretty quick.